So there we had the probability of A given us 1/2, the probability of B given us 1/3, and the probability of A union B given us 2/3. Then we checked if they are independent. We found that they are independent. Now 2 of B, we'll check if they are mutually exclusive. The mutually exclusive is the same as saying that the probability of A intersection B is 0. So anyway, we checked. We found that the probability of A intersection B is not 0. So two events, A and B, are said to be mutual.
May you please go back to the previous screen?
I cannot retrieve the previous screen in the previous session.
Okay.
So two events A and B are said to be mutually exclusive if they can occur at the same time, meaning if the rate of A intersection B is equal to 0. So in the case of our question, the probability of A intersection B was found to be 1/6, which is not equal to 0. Hence, A and B are not mutually exclusive. They are not mutually exclusive. What we are saying here is that two events will be exclusive. They cannot occur. It can't be seen anyway. Unless scientific advice is not true. Unless the correct. So now what it is, if it's mutually exclusive, then the probability if you use X of NB, you see, then you probability A plus probability plus probability C. And if A and B are not mutual, then if A the probability of A union B is equal to the probability plus the probability yes, the probability in the second and probability in the second. Okay, 1, 2, 3. So A of B is success. B is success. Part of A probability of B minus you remove the bit of A intersection. That means the probability of A intersection C minus the bit of A intersection C. You remove A, C, remove A intersection C, then you remove again the bit of A intersection C. Then minus the probability of B intersection C. You added the 3 times and the 3 times. You need to make the bit of A and B intersection. After the A intersection B twice, so remove it once. And B intersection. Section, still have the intersection this one. To come back and see. See. You added section C twice. So you remove it. Then in each removing A and B. So you add the 3 times and remove 3 times, saying that it's not there. So you need to add it back.
So, but why is it moving probability of intersection B intersection B to move the other probability?
These ones we remove it even just when I you add twice, remove this one once. It's just an addition. Between A and B, you cannot add numbers. So there on an event mutual, let's say give a reason also independent. So the reason is coming here. The probability that B is 1 is not 0. So A and B are mutually exclusive. Equally, we did independent also say that also A intersection that is not 2. Yeah, then there's no exclusiveness. And that's the definition. Let's go to question 2. So now we already have terms. So given that for two events R and S, the probability of R is 0.3. The probability of R union S is equal to 0.6. Find the probability of S and the probability of R. So find probability of S when R and S are in one mutually exclusive. So the question says find the probability of S and the probability of S of R intersection S when in case R and S are mutually exclusive. So let's see that's the probability of S. So we'll say the probability of S is 0.6 minus 0.3, which is equal to 0.3. Then part 2, if two events are independent. So if R and S are independent. When do we say two events are independent? When the probability of their intersection is the same as the probability of A of R, probability of S. So here, if they are independent and want to find the probability of S, then we'll say the probability of S is equal to the probability of R intersection S over the probability of R.
So,
Hello?
like, how did you find probability of S? Did you do it together with the R intersection S or what?
R intersection S, if they are mutually exclusive, is 0. And they are still mutually exclusive, we want to find the probability of S. So since the intersection is 0, it won't appear in the formula of union S, R union S. And then you take R on the other side, you remain with PS. Probability of S is 0.6 minus 0.3.
Thank you.
Okay. So now on the independence, if the two are independent, how do we find the intersection? Or how do we find the missing one? So we know that the independence is the probability of R intersection S is the probability of R plus the probability of S minus the probability of R union S. Okay, so it means that here where we have the probability of R intersection S, we can have the probability of R plus the probability of S minus the probability of R union S, and everything divided by the probability of R.
Dad, don't you have The previous said you multiplied. You said probability of R intersection S is equal to probability of R multiplied by probability of S. How come now using this thing?
No, we would have multiplied if we had both probabilities. Now in the formula, there's probability of R intersection S, which we don't have here. There's also the probability of R, which we have, but probability of S we don't have. So we have two things missing.
Okay.
So for the intersection, now we are using this one here. So we know the probability of R is 0.3. Plus the probability of S we don't know, but we know the probability of R union S is 0.6. And then we are multiplying by the probability of R, which is 0.3. This is the probability of S. So we cross multiply, we have 0.3 probability of S is equal to negative 0.3 plus the probability of S. And then take this guy the other side so that we have 0.3 positive, and take this guy the other side so that we have the probability of S minus 0.3. And then probability of S, we factorize it now, we'll have 1 minus 0.3 remaining. So we'll have the probability of S is equal to 0.3 divided by 0.7. And this is equal to 0.3 divided by 0.7, 0.4285. Something like 0.43. Because we do independent, that is not zero product.
Maybe repeat explanations. I will.
Another one say something.
I was asking that to find the probability separately.
Yes, it was asking us find the probability of S if R and S are independent. So mutually we find the probability of intersection and the probability of S. Then it's done that one. What if they are independent? So now if they are independent, you are saying you're going to extract the information from the fact that independence means that R intersection S probability should be the same as the probability of R multiplied by the probability of S. And then after that, you say, okay, now you don't have the probability of S. You also don't have the probability of the intersection. But the intersection has a formula. In the formula of the intersection, we have the probability of R plus the probability of S minus so this will cancel. It's my home.